So here is Unit 3, Lesson B on projectile motion. To start with, we have a question here. During a movie stunt, a car is driven straight off the edge of a bridge to a river below. At the same moment that the car leaves the bridge, a movie hero who is hanging off the side of the bridge lets go and drops down straight into the water. Who hits the river first? So the situation is this. At the moment that the car leaves the bridge horizontally and travels to the water below, the person lets go and drops at the same time. The question is asking, which one of these two objects hits the ground first? Or will they hit the ground at the same time? We should be able to answer this question from this lesson. So projectile motion involves what's called a projectile. A projectile is any object that falls through the air. Projectiles are accelerated downward by the force of gravity, so that their magnitude of their acceleration is that of g, okay, 9.8 meters per second squared. Now, while projectiles are affected by their passage through the air to varying degrees, we're going to be ignoring the effects of air resistance in all of the problem situations we deal with. And that can be safely done as long as the object is dense and the distance that it falls is not too great. Now, projectiles will always follow a curved path called a trajectory. A trajectory is a segment of a parabola, which is a fact that was discovered by Galileo. Sometimes a trajectory is called a ballistic path. Now, in reality, such motion is really three-dimensional, but we're going to be simplifying the situation and dealing with only two dimensions, the back and forth horizontal direction and the up and down vertical direction. So to understand projectile motion, we're going to start by examining this picture right here. Okay? In this picture, we've got two balls, a red ball and a yellow ball. Both were launched at the same point at the same time. Okay? Red ball dropped straight down. Yellow ball was launched horizontally, so it came out. As we can see vertically in this situation, both balls are at the same position at the same point in time all the way down as they fall downward. Okay? We can look across, and every time the balls are at the evenly spaced positions on their vertical downward trip. But now let's consider the components of the motion of the yellow ball. This ball undergoes the same horizontal displacement during each time interval. We can tell that from these red lines that are spaced evenly apart. At this point here, at this earlier point during the ball's trip, the red lines are this far apart. They do not change as the ball moves to a different position. What this indicates to us then is this yellow ball experiences a constant velocity in this horizontal direction while falling and increasing its velocity in the downward vertical direction. Now, this is really the big key point to all projectile motion. Projectiles accelerate vertically at negative 9.8 meters per second squared. Projectiles move with constant velocity in the horizontal direction. And this is really the biggest point of projectile motion right now. So this is how this looks mathematically. Okay, so the vertical motion of a projectile is given to us by our kinematics equations, where we've got the object is in free fall. The horizontal motion of the projectile, though, is given to us by our constant velocity equation. The key to efficiently deal with projectile motion is to simply break the velocity down into its horizontal and vertical components. Vectors that are perpendicular to each other act independently, which we've seen previously. This is so important. We're going to write that. You're going to show it right here in big, large, friendly letters. Vectors that are perpendicular to each other act independently to each other. Okay, so what we can do when we have a projectile is we're going to be breaking it down into its x component and y component, and then deal with the motion vertically and horizontally separately, knowing that a projectile, so if I take a ball and I launch a ball from one place to another, the thing is going to go up and down in the same amount of time that it goes out. Okay? So while we can take the initial velocity of a projectile and break it into its y component and its x component, those components of the velocity are linked in time. Okay, so it's going to take the same amount of time for a projectile to go up and back down as it does for that projectile to go out horizontally, like that. The two types of projectile motion that we're going to be primarily dealing with will be what's called a horizontal launch. That's this picture here, where the object is launched from a horizontal position, so it's given only an initial velocity in the x direction, where that x direction velocity is constant throughout the trajectory, and it falls down. And then we'll also look at angled launch problems, where we've got a projectile launched on a level ground from one point to another. In this case, we're still going to have a constant x velocity, but our y velocity is going to decrease as it goes up and increase as it comes down. So let's begin with looking at horizontal launch problems. In a horizontal launch problem, the horizontal velocity is always constant. The initial vertical velocity is always 0. And the acceleration in the vertical direction is always g, 9.8 meters per second squared, down. So this picture right here is showing a projectile launched horizontally at a velocity, an initial velocity of 20 meters per second. It's always showing 20 meters per second in that horizontal direction. However, in the vertical direction, it's, after 1 second, it's at 9.8 meters per second. Then it's at 19.6 meters per second. It's 29.4 meters per second. 39.2 meters per second. And then finally, 49 meters per second after 5 seconds here. So if we wanted to know, say, like the final velocity of this thing, that would be the final velocity before this object hits the ground down below. We just look at those vectors, and these are vector components sitting here, so we could just figure out the resultant vector by Pythagorizing this, and we'd get the magnitude of that final velocity. So now, while there are several equations, kinematics equations, that we could use to solve projectile motion problems, in a horizontal launch situation, there are 3 common situations that you will see, and we're only going to be using 2 equations to solve horizontal launch problems. The first is our second kinematics equation, the yf equals yi plus vyit minus 1/2 gt squared. Now in this equation I've changed the vi right there to a vyi because I'm talking specifically about the y direction and the initial velocity in that y direction. And then we've got vx equals delta x over t. That is our constant velocity equation. So these are really the only 2 equations that you would use in a horizontal launch situation. There's 3 problem situations that are common. The first is this, where we are given the horizontal launch velocity and we're given the height of the table or building or cliff or whatever we're launching this projectile off of. In order to solve for this problem, you would first use the second kinematics equation to find the amount of time it takes for the projectile to land, and then use the constant velocity equation to figure out how far out it goes. We're looking for the range or the distance away from the building, cliff, whatever. In the second problem-solving situation, you are given the horizontal velocity, and you're given the range, and you're asked to find the height. To solve this, you would first use the constant velocity equation to find the amount of time down. Okay, so this is the situation where you'd use this equation first to find the amount of time down, and then use the kinematics equation to find the height. The third situation that we would deal with is where you are given the height, You're given the horizontal distance and you're asked to find that initial velocity. In that situation, you would use first the second kinematics equation to find the time down and use the constant velocity equation to find that horizontal velocity. Okay, so you can see kind of a pattern involved in all three of these types of problems involving horizontal launch. You're always going to first be using something to find the time that it takes to land, and then use something else to find the information you're looking for. So let's look at an example. The Royal Gorge Bridge in Colorado rises 321 meters above the Arkansas River. Suppose you kick a rock horizontally off the bridge. The magnitude of the rock's horizontal displacement is 45 meters. We want to find the speed at which the rock was kicked. And looking at the information we're given here, the bridge is 321 meters tall. There's our height. And the displacement, horizontal displacement, is 45 meters. That's our range. We're asked to find that horizontal velocity. That's this type of projectile motion, horizontal projectile motion problem. So we're first going to use our second kinematics equation, and then to find the time, and then use that time in the constant velocity equation. So when we go to find that time, right, we remember that we've got horizontal launch, so our initial velocity in the y direction is always 0. We plug this through, we find our time to be this 8.09 seconds. So then all we need to do is plug into our constant velocity equation to find that our initial velocity was 5.6 meters per second. That was the velocity at which this rock was kicked horizontally off the bridge. Okay, so now let's look at angled launch problems. When I launch an object at an angle, I'm giving it some initial velocity at an angle to the horizontal. That means that this velocity vector is split into its x component and its y component. So it now has an initial velocity in the y direction, and it has a velocity in the x direction. Throughout its motion, it's going to move horizontally at a constant speed. So this x velocity is never going to change. The key to angled launch problems is how you begin them. When you get an angled launch problem, the first thing that you want to do is always split your velocity, your initial velocity, into its components. The problems that you will see then will always be split, so your horizontal velocity will always be Vx equals V cosine angle. That angle is the angle of launch. Vyi, this is going to be your initial velocity in the y direction, will always be V sine theta. Okay? They're always going to be that. I'm always going to set up problems so that that is what you see. Okay? And so the first thing to do in any angled launch problem is to get your components. Then you have to recognize and remember that as long as the projectile is in the air, it's going to move horizontally at a constant speed. It's going to accelerate downwards at a constant rate of g, and at the top of its path, the vertical velocity will be 0, the horizontal velocity will be constant, and the final vertical velocity will be equal to the initial vertical velocity, but point in the opposite direction. So what that means is this velocity right here, that final y velocity, will equal the initial y velocity, but be in the opposite direction. So you can see from this diagram that once this thing is launched, horizontal velocity is constant. Vertical velocity decreases as it rises up, increases as it falls back down. Okay, so example number 5. This is a different example than what's in your reading packet, so you should copy it down in your notes. A football is kicked with an initial velocity of 20 meters per second at an angle of 40 degrees. How far does it go? So this thing is kicked at 20 meters per second, angle of 40 degrees. The first thing to do is going to be to split its velocity into its components. We're going to have Vx, which is V cosine angle, and we'll have VYI, its initial velocity in the y direction, which will be V sine theta. So its velocity in the x direction will be 15.32 meters per second. Its velocity in the y direction will be 12.86 meters per second. Okay, so we're asked, this thing is kicked and it goes out something like that, and we're asked to find out how far it goes. That's what we want to know. Okay? Well, what's true about angled launch problems like this, where they're on level ground, is that the amount of time that it takes to get to its highest point right here is going to be equal to the amount of time that it takes to get to its furthest point out. Okay? So the time up will equal the time down. Okay? So we can use that fact to help us solve this problem. So again, we're kind of doing the same type of formula as we did, same type of basic procedure as we did with horizontal launch problems, where we're trying to find a time first and then a distance. Because we know that in the vertical direction this thing's really going in with free fall, we're going to use our free fall kinematics equations. At this highest point then, its velocity in the y direction will be 0. Its initial velocity in the y direction we found to be this 12.86. Its acceleration in the y direction is 9.8 meters per second squared, and we can find the time to the highest point. When we do that, we find that the time to the highest point is 1.31 seconds. Okay? Well, the time to this highest point will equal the amount of time it takes to come all the way back down, so we double that for the total time of our trip. And we get a total time of 2.62 seconds. Now we want to find the range. We want to find out how far it will go. How far it will go means the horizontal direction here. We recognize right away that our velocity in the horizontal direction is a constant, 15.32 meters per second, and we're going to use just this constant velocity equation right there. We plug in our values and we get a range of 40.2 meters. That's how far the ball went. Okay, so that's horizontal launch and that's angled launch. We'll see you in class.